In continuum mechanics, a fluid is said to be in hydrostatic equilibrium or hydrostatic balance when it is at rest, or when the flow velocity at each point is constant over time. This occurs when external forces such as gravity are balanced by a pressure gradient force. For instance, the pressure gradient force prevents gravity from collapsing Earth's atmosphere into a thin, dense shell, whereas gravity prevents the pressure gradient force from diffusing the atmosphere into space. Hydrostatic equilibrium is the current distinguishing criterion between dwarf planets and small solar system bodies, and has other roles in astrophysics and planetary geology. This qualification typically means that the object is symmetrically rounded into a spheroid or ellipsoid shape, where any irregular surface features are due to a relatively thin solid crust. There are 31 observationally confirmed such objects, sometimes called planemos, in the Solar System, 7 more that are virtually certain, and 100 or so more that are likely. Mathematical consideration equals derivation from force summation equals, Newton's laws of motion state that a volume of a fluid that is not in motion or that is in a state of constant velocity must have zero net force on it. This means the sum of the forces in a given direction must be opposed by an equal sum of forces in the opposite direction. This force balance is called a hydrostatic equilibrium. The fluid can be split into a large number of cuboid volume elements. By considering a single element, the action of the fluid can be derived. There are 3 forces: the force downwards onto the top of the cuboid from the pressure, P, of the fluid above it is, from the definition of pressure. Similarly, the force on the volume element from the pressure of the fluid below pushing upwards is. Finally, the weight of the volume element causes a force downwards. If the density is I, the volume is V and G the standard gravity, then the volume of this cuboid is equal to the area of the top or bottom, times the height the formula for finding the volume of a cube. By balancing these forces, the total force on the fluid is. This sum equals 0 if the fluid's velocity is constant. Dividing by A. Or top or bottom is a change in pressure, and h is the height of the volume element a change in the distance above the ground. By saying these changes are infinitesimally small, the equation can be written in differential form. Density changes with pressure, and gravity changes with height, so the equation would be equals derivation from Navier-Stokes equations equals. Note finally that this last equation can be derived by solving the 3-dimensional Navier-Stokes equations for the equilibrium situation where. Then the only non-trivial equation is the equation, which now reads. Thus, hydrostatic balance can be regarded as a particularly simple equilibrium solution of the Navier-Stokes equations. Equals derivation from general relativity equals, by plugging the energy-momentum tensor for a perfect fluid into the Einstein field equations and using the conservation condition, one can derive the Tolman-Oppenheimer-Volkoff equation for relativistic stellar structure. In practice, I and I are related by an equation of state of the form F, I equals 0, with F specific to makeup of the star. M, R, is a foliation of spheres weighted by the mass density I, R, with the largest sphere having radius r. Per standard procedure in taking the non-relativistic limit, we let R, so that the factor. Therefore, in the non-relativistic limit the Tolman-Oppenheimer-Volkoff equation reduces the Newton's hydrostatic equilibrium. We have made the trivial notation changed h equals r and have used F, I equals 0 to express I in terms of P. Applications equals fluids equals, the hydrostatic equilibrium pertains to hydrostatics and the principles of equilibrium of fluids. A hydrostatic balance is a particular balance for weighing substances in water. Hydrostatic balance allows the discovery of their specific gravities. Equals astrophysics equals, in any given layer of a star, there is a hydrostatic equilibrium between the outward thermal pressure from below and the weight of the material above pressing inward. The isotropic gravitational field compresses the star into the most compact shape possible. A rotating star in hydrostatic equilibrium is an oblate spheroid up to a certain angular velocity. An extreme example of this phenomenon is the star Vega, which has a rotation period of 12.5 hours. Consequently, Vega is about 20% larger at the equator than at the poles. A star with an angular velocity above the critical angular velocity becomes a Jacobi ellipsoid, and at still faster rotation it is no longer ellipsoidal but piriform or oviform, with yet other shapes beyond that, though shapes beyond scalene are not stable. If the star has a massive nearby companion object, then tidal forces come into play as well, distorting the star into a scalene shape when rotation alone would make it a spheroid. An example of this is Beta Lyrae. Hydrostatic equilibrium is also important for the intra-cluster medium, where it restricts the amount of fluid that can be present in the core of a cluster of galaxies. We can also use the principle of hydrostatic equilibrium to estimate the velocity dispersion of dark matter in clusters of galaxies. Only baryonic matter emits X-ray radiation. The absolute X-ray luminosity per unit volume takes the form where and the temperature and density of the baryonic matter, and is some function of temperature and fundamental constants. The baryonic density satisfies the above equation. The integral is a measure of the total mass of the cluster, with being the proper distance to the center of the cluster. Using the ideal gas law and rearranging, we arrive at multiplying by and differentiating with respect to yields. If we make the assumption that cold dark matter particles have an isotropic velocity distribution, then the same derivation applies to these particles, and their density satisfies the nonlinear differential equation. With perfect X-ray and distance data, we could calculate the baryon density at each point in the cluster and thus the dark matter density. We could then calculate the velocity dispersion of the dark matter, which is given by the central density ratio is dependent on the redshift of the cluster and is given by where is the angular width of the cluster and the proper distance to the cluster. Values for the ratio range from 0.11 to 0.14 for various surveys. Planetary geology The concept of hydrostatic equilibrium has also become important in determining whether an astronomical object is a planet, dwarf planet, or small solar system body. According to the definition of planet adopted by the International Astronomical Union in 2006, planets and dwarf planets are objects that have sufficient gravity to overcome their own rigidity and assume hydrostatic equilibrium. Such a body will normally have the differentiated interior and geology of a world, though near hydrostatic bodies such as the protoplanet 4 Vesta may also be differentiated. Sometimes the equilibrium shape is an oblate spheroid, as is the case with Earth. However, in the cases of moons in synchronous orbit, near unidirectional tidal forces create a scalene ellipsoid, and the dwarf planet Haumea appears to be scalene due to its rapid rotation. It had been thought that icy objects with a diameter larger than roughly 400 km are usually in hydrostatic equilibrium, whereas those smaller than that are not. Icy objects can achieve hydrostatic equilibrium at a smaller size than rocky objects. The smallest object that appears to have an equilibrium shape is the icy moon Mimas at 397 km, whereas the largest object known to have an obviously non-equilibrium shape is the rocky asteroid Pallas at 532 km. However, Mimas is not actually in hydrostatic equilibrium for its current rotation. The smallest body confirmed to be in hydrostatic equilibrium is the icy moon Rhea, at 1,528 km, whereas the largest body known to not be in hydrostatic equilibrium is the icy moon Iapetus, at 1,470 km. Because the terrestrial planets and dwarf planets have irregular surfaces, this definition evidently has some flexibility, but a specific means of quantifying an object's shape by this standard has not yet been announced. Local irregularities may be consistent with global equilibrium. For example, the massive base of the tallest mountain on Earth, Mauna Kea, has deformed and depressed the level of the surrounding crust, so that the overall distribution of mass approaches equilibrium. The amount of leeway afforded the definition could affect the classification of the asteroid Vesta, which may have solidified while in hydrostatic equilibrium but was subsequently significantly deformed by large impacts. Atmospherics In the atmosphere, the pressure of the air decreases with increasing altitude. This pressure difference causes an upward force called the pressure gradient force. The force of gravity balances this out, keeping the atmosphere bound to Earth and maintaining pressure differences with altitude. See also, List of solar system objects in hydrostatic equilibrium, statics, tube balloon experiment. Notes. References: White, Frank M. Pressure distribution in a fluid. Fluid mechanics. New York, McGraw-Hill pages 63-107. ISBN 978-0-07-128645-9. External links: Stbell, Nick Stbell's Astronomy Notes.